general relativity step by step. I'm going to combine everything that we've got here into one uber equation called the Lorentz transform. Lorentz transform. And basically what I'm going to do is to give a rule whereby we can work out, I'm going to zoom in a little bit, t bar x bar equals some function of t and x, and what I'm going to do is map it onto a linear matrix A, B, C, D. Uppercase you'll notice, because if I use lowercase you'll think that that C is a speed of light and it'll drive you nuts. And A, B, C, D to be determined. I'm going to find out what they are. Yes. So the way I'm going to do this is by choosing very, very simple vectors and transform them and see what they look like. So I'm going to choose that. I guess if you wanted to draw it, it looks like this here. If that's the space axis and that's time, that looks like that, because we've got a unit. We've got t in the time direction here. 0 and x, which of course looks like this, and I'm going to choose 1, 1, which is from the origin is a light path. So I'm going to choose a time-like displacement, I'm going to choose a space-like displacement, and I'm going to choose a null or a light-like displacement. And that should be enough for us to figure out what the quantities are. Okay, it's very, very liable to get this wrong, so I'm going to cut it up into small chunks of screencast, because I'm not going to attempt to do it all in one, because if I do, it takes about 25 minutes, and after 22 minutes I get it all wrong and have to start again. So that's why I'm going to cut it up into bits. Okay, so what colour am I? Red. I'll have to go back to black. Here it is. Right. A, B, C and D. So I'm going to use this one, T0, and this is equal to T bar X bar, which is coordinates as calculated by our friend in a spaceship. Let me draw that spaceship again. There's the spaceship, and it's moving this way, and so this person here constructs a T bar axis there and an X bar axis there. And as far as he's concerned, his description of a point is related to the black coordinates description by this framework here. Equals A, T, and then this one here is C, T, I guess. So T bar equals A, T, and X bar equals the bottom one, which is just C, T. And we know what A is already, because we've set up this photon clock here. It's many screencasts ago, but we set out a photon clock here, and so our person was counting time by how many bounces backwards and forwards by this laser light here. Whereas his friend in the spaceship, there it was, cruising along here, what does he see? He sees the mirrors moving. There are the mirrors. It's the same mirrors, but just observed by this chap in his spaceship here. And the light beam is doing that diagonal path there. And so that means that we know A equals 1 over root 1 minus beta squared, where beta equals v over c equals the normalized velocity, or normalized speed. Whew. Okay, so that's quite nice. So we've done A already. We need to do the other guys now. Okay, so how do we proceed? Well, what do? Is we work out delta s squared, which is minus delta t squared plus delta x squared, and there's a y and a z, of course, if you really want. And so in the unbarred coordinate system, that's just minus t squared. So it's a perfectly respectable time-like interval, because it's minus the square of something, so it's negative. What does delta s bar squared equal? Well, that's minus delta t bar squared plus delta x bar squared equals minus a squared t squared from here plus c squared t squared from here. That's this thing here is delta t squared, delta t bar squared, excuse me, and this one here is delta x bar squared. So minus t squared equals minus a squared t squared plus c squared t squared. So provided t is not equal to 0, minus 1 equals minus a squared plus c squared. C squared equals a squared minus 1. Yeah. Equals gamma squared minus 1. And this is typical relativity, this, because it gets awfully messy. 1 over root 1 minus beta squared, all squared, minus 1, just expanding for gamma. 1 over 1 minus beta squared, minus 1 minus beta squared over 1 minus beta squared, equals 1 minus beta squared, 1 minus 1 plus beta squared. So that tells me that c squared equals beta squared over 1 minus beta squared. See, it's messy. It's messy. And so c equals plus or minus beta over root 1 minus beta squared equals plus or minus beta gamma. And I'm going to choose the positive solution to indicate that I'm moving right to left, because I've got two choices here. You can either be moving left to right or right to left. I'm just going to choose moving right to left. There it is. So my matrix, which was A, B, C, D, I've now got two things. I've got A and C, which is now gamma, beta gamma, and these two ones here are as yet unknown. So my transform is T bar X bar equals gamma, capital B, which is unknown, beta gamma, which we worked out from the invariance of the interval, D, which is still unknown, Tx. And I'll work out what capital B and capital B are in the next screencast. So I'm going to stop there. Stop.